Okay, hello. Today I'm going to go through introductory abstract algebra problem from Joseph Gallian's Contemporary Introduction to Abstract Algebra. But really at the end of the day, this is just a number theory problem. And in order to tackle it, we need to use these following tools. First, how to represent the greatest common divisor as a linear combination. In words, for any non-zero integers a and b, there exist integers s and t such that the greatest common divisor of a and b is as plus bt, and this number is the smallest possible number you can get by the low ordering principle. Now, formally, if you want to write this in quantifiers, it's like this, but the only thing pedagogically that you need to pay attention to is that the existence, the quantifier that is to the rightmost, is the one that matters for this particular case. Now, we might have different things for different nesting orders of quantifiers, but I'm not really good at this, so you're just going to have to trust my word for here and now. And I'm going to say without proof that there's a corollary. If they are relatively prime, then the greatest common divisor you get is essentially 1. So this sequence equals 1 for a particular s and t that we need to find. Now, the question of interest. Show that 5n plus 3 and 7n plus 4 are relatively prime for all integers n. The first method, which will only work if you're really good with balancing out like two expressions together, is trial and error, essentially. We want to find specific integers s and t that basically make the greatest common divisor of this, and essentially this expression, equal to 1. Now, I happen to play around and I get that s equals 7 and t equals negative 5 works for this. You can check the arithmetic for this here. Follow line by line, and you end up getting 1. So this proves that this is true for all n. We didn't even have to refer to anything with n. We just had to manipulate s and t. The reason I think we were really lucky is because like the remainder of one sequence is 3 and the other is 4, and those just are apart by a distance of 1 unit. However, if you want to figure out where this s and t come from, well, I'm sorry, but unfortunately you're just going to have to use the extended Euclidean division algorithm, which is a pretty tedious recipe step. In abstract, it looks like this. Consider the greatest common divisor of a and b. A and b are not the same number, so by transitivity and ordering, one number must be bigger than the other. Good. The number that is bigger is the dividend, what you're dividing out of. Think of like a big giant pizza pie. And b is the divisor. Think of like how many slices of pizza you're chopping out. And in this algorithm, with the freedom for us to choose whatever our quotients could be, we want this quantity to head to 0 as fast as possible. So by the division algorithm, let a equals b q1 plus r1. And it follows this inequality here, which follows through the logic of the Euclidean division algorithm, which my best advice on how to understand that is through understanding pie charts, with the possibly unintuitive fact that a whole pizza pie or remainder of 0 is the same thing as a whole pizza pie with all those slices in mod n. It's yeah, it's hard, but you'll basically get that dividends are basically your new divisors, and your new divisors are the previous remainders. And if you go and write it, it's a good practice to write them down line by line. You eventually derive this more general expression here. Once you reach a critical divisor where the remainder is 0, this last remaining divisor, Rn minus 1, that is the greatest common factor of the two numbers a and b. Now, that was a bit way too abstract, so let us go and practice with a numeric concrete example. Not original. I found this somewhere on Stack Exchange. So 888 is clearly greater than 54. Now we are going to divide 888 by 54. You do it by calculator the like. We get a remainder of 24, with 16 being the largest. Therefore, 54 becomes our new dividend, and 24 becomes our new divisor. 54 divided by 24 here. We get 2 times 24 goes in there, but it leaves us a remainder of 6. Do it one more time. Oh, 24 is divisible by 6. We are done. So the greatest common divisor of 885 and 54 is 6. Now back to actually solving our problem. We need to test the ordering of 7n plus 4 and 5n plus 3. There are more n's in 7n than 5n, so we can break this up into 5n plus 2n. And then we can make an easy comparison, which clearly shows us that this is greater than 5n plus 3. Now we apply the extended Euclidean division algorithm to this. 7n plus 4 equals 5n plus 3. Again, we want the quantity to head towards 0 as fast as possible. We have the freedom to pick whatever integer qi quotient we can use to make this happen efficiently. For this case, it's q1 equals 1. Take the difference of these terms, and you'll get 2n plus 1. Okay, now the new dividend will be 5n plus 3. The new divisor will be 2n plus 1. Repeat the process. Q2 has to be 2, because 2 times 2n is 4n. That goes in there enough. Do the difference of this, and I get n plus 1. And there's a 2n plus 1 somewhere. Did I mistype? Oh, yeah, no, that was this old thing here. So then 2n plus 1 is the new dividend, n plus 1 is the new divisor. Repeat the same process. And yeah, q3 is 1. Boom, boom. Voila, we get n plus 1 equals n plus 1. N plus 1 minus n equals 1. Stop. Stop. We are done. Now the ugly part, we have to resubstitute everything back. And I did in the most careful way possible of highlighting and coloring where we make the substitutions. Otherwise, any other supplementary steps that you see here is the result of redistributing factors and multiplying by various powers of -1. The factoring of -1, multiplying by powers of -1, I can see to be the biggest source of error where one might make mistakes when doing these sorts of problems. Unfortunately, negative numbers are so important in algebra because they're an additive and multiplicative inverse. And if we didn't have those things, well, math wouldn't be as beautiful and complicated as it is today. So you just gotta be careful with this, I'm afraid, unfortunately. But here's one substitution for 1 we're making, a back substitution for n here. Here's a third back substitution. These are basically string lines of algebra manipulation. A back substitution for 2n plus 1, and then more algebra again. So in total, there were 4 back substitution methods. Substitutions we needed to make. Which means the algorithm lasted for 4 steps. And if you're an expert with algorithm complexity, you can try and guess or deduce what kind of complexity time that is equivalent to. But I'm not an expert at that at all. And I'll just leave it that to end for today. But yes, that is where the 7 and the -5 comes from. But once you put those, going back to the original problem, once you deduce that that the integers you need are 7 and -5, you just put these in here and show that you get 1, and that completes the proof. And yep, I am at the end of my rope. So I'll end this video now. Thank you.